In this lecture, we are going to derive the recursion formula for Euler's method, which is a method for approximating the solution to a first-order initial value problem. Euler's method is also frequently called the simple Euler method. Let y equals y of t be the solution to the initial value problem given by the differential equation y prime of t equals f of ty, with y of a equal to y sub 0. Suppose we are looking for an approximation for y of b where b is greater than a. We partition the interval from t equals a to t equals b using the partition points or nodes t sub 0, which we set equal to a, t sub 0 is less than t sub 1, t sub 1 is less than t sub 2, etc., 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 all the way to t sub n, which we set equal to b. To simplify the discussion, we will assume a uniform partition of the interval from t equals a to t equals b, so that the step size or distance between consecutive nodes is a constant delta t. We designate this step size as h. H is equal to b minus a divided by n. Given that y of t sub 0 or y of a is equal to y sub 0, we first approximate y of t sub 1. To find an approximation for y of t sub 1, Euler's method uses the tangent line to the solution curve at t equals a or at t equals t sub 0. Let the tangent line at t equals t sub 0 be given by L sub 0 of t. L sub 0 of t is equal to y of t sub 0 plus the slope of the tangent line. The slope of the tangent line is y prime evaluated at t sub 0, and this is given by f of t sub 0, y of t sub 0. We multiply this slope by t minus t sub 0. Y of t sub 0 is y sub 0, so that L sub 0 of t equals y sub 0 plus f of t sub 0, y sub 0, times the quantity t minus t sub 0. We find the value of L sub 0 of t at t equals t sub 1. L sub 0 of t sub 1 is Euler's method's approximation for y of t sub 1. Let y sub 1 be L sub 0 of t sub 1, so that replacing t by t sub 1, y sub 1 equals y sub 0 plus f of t sub 0, y sub 0 times the quantity t sub 1 minus t sub 0. T sub 1 minus t sub 0 is the step size h, so that y sub 1 equals y sub 0 plus f of t sub 0, y sub 0 times h. We repeat the process to find an approximation, this time for y of t sub 2. Let L sub 1 of t be the linearization of y of t at t equals t sub 1. L sub 1 of t is equal to y of t sub 1 plus the slope y prime of t sub 1. Y prime of t sub 1 is equal to f of t sub 1, y of t sub 1. And we multiply y prime of t sub 1 by the quantity t minus t sub 1. We do not have the exact value of y of t sub 1, so we use what is available to us, and that is the approximation y sub 1 of y of t sub 1. And so in L sub 1 of t, we replace y of t sub 1 by y sub 1. We should point out that L sub 1 of t with this substitution gives only an approximate tangent line to y of t at t equals t sub 1. L sub 1 of t sub 2 is the method's approximation for y of t sub 2. L sub 1 of t sub 2 equals y sub 1 plus f of t sub 1, y sub 1 times the quantity t sub 2 minus t sub 1. And t sub 2 minus t sub 1 is h. Let y sub 2 be equal to L sub 1 of t sub 2, so that y sub 2 equals y sub 1 plus f of t sub 1, y sub 1 times h. We generalize this to get the recursion for Euler's method. If y sub k is the method's approximation for y of t sub k, then y sub k equals y sub k minus 1 plus f of t sub k minus 1, y sub k minus 1 times h. K goes from 1 to n. It is also sometimes more convenient to write the recursion in the following way. Y sub k plus 1 equals y sub k plus f of t sub k y sub k times h, in which case k goes from 0 to n minus 1. With b being equal to t sub n, y sub n will be the method's approximation for y of b.